Okay. Good morning. Okay. So in this class, we'll discuss trees and its properties. Okay. So, okay. So a graph having no cycle is said to be acyclic. So the first definition of acyclic graph. Okay. So a graph without a cycle. Okay, is said to be acyclic. Similarly, next definition is a forest. A forest is a acyclic graph. Okay. So next definition, a tree. A tree is connected acyclic graph. Okay. So connected. Okay. Tree. So connected. I think in the last class we discussed what is connected graph. Connected plus no cycle. Okay. Or no cycle or acyclic. 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 Okay. Or you can say it is what? No cycle. So implies the graph is that tree. Okay. So, so connectedness and it has no cycle. Then we say that graph is what? Tree. Okay. Also, what do you mean by forest? Actually, forest is only what? As, only acyclic. That means what? It is not connected. Okay, forest. Okay, a forest is an acyclic graph means it satisfies only this part. It means the forest has no cycle. So and hence the forest is what? Not connected. Okay. Next definition. Okay, these are some of the examples for trees because it is a connected graph and has no cycle. This is also connected graph and it has no cycle. This is also connected graph and it has no cycle. So these are all example for trees. Okay. So these are example for not trees because it is connected but it has a cycle. That's why it is not a tree. Similarly, this is what connected but it has a cycle. That's why this is also what not a tree. So next is spanning tree. So we know spanning subgraph already. Okay, spanning subgraph. So yeah, subgraph H of G is a spanning subgraph if the vertex set of that subgraph is equal to vertex set of H is equal to what? Vertex set of G. But edge set is already told to you the edge set of H is a uh, edge set of H. How I told last class. Edge set is edge set of H may be proper or it may be what equal to edge set of what G. So that is the meaning. That's why they don't write here. Okay. So this condition is itself enough. Okay. Next, what is spanning tree? Now, yeah, first it should be a spanning subgraph. Okay, which is also a tree. Okay, so I explained what is spanning subgraph. So first is a spanning tree should be a first spanning subgraph, which is also a tree. So that means a spanning subgraph without cycle is a tree. Okay. Now I will give you an example. So this is K5, complete graph with what? 5 vertices. So this is a spanning subgraph of what? This K5. So A, B, C, D, E. Okay. So this is a spanning subgraph of spanning subgraph. Why? Because the vertex set is what? Vertex set of K5 and the vertex set of this graph C5 are what? Same. So that's why this is what? Spanning subgraph of this graph. But this is not a spanning tree because it contains what? A cycle. But this one A, B, C, E, D. So this is actually spanning tree of this graph because it contains all the vertices A, B, C, D, E, but it does not contains what? A cycle. So that's why this is a spanning tree of this graph. Similarly, this is also A, B, C, D, E. Okay, this is also a spanning tree of this graph because it contains all the vertices and also it has no cycle. Okay, the next idea is, suppose if the graph is given, to find the number of spanning trees of a given graph with n vertices. So just you should know what total number of spanning trees of a graph with n vertices is n power n minus 2. For example, uh, k equal to, for example, k3. K3 means what? This is k3. So n equal to what? 3 here. N equal to 3 now. So n power n minus 2. N power n minus 2. N power 3 minus 2. So what is n? 3. 3 power 3 minus 2 spanning trees. So that means what? 3 spanning trees. Okay. So this is actually 1. Okay. Wow. This is 1, 2, 3. Okay. Wow. 1, 2, 3. Another one is 1, 2, 3, like this. Okay. 1, 2, 3. This is another spanning tree. So next one is this one. 1, 2, 3. Okay, so totally 3 spanning trees. Similarly, you can take n equal to 4. So just I will tell the numbers only. What is n power n minus 1? N power n minus 2. N power n minus 2. So n power n minus 2 means 4 power 4 minus 4 power n minus 2. 4 power 4 minus 2. Yeah, 4 power 4 minus 2. 4 power 4 minus 2 is 4 square. 4 square is equal to 16 spanning trees you can draw. Okay. Okay. So just you should know this thing. Okay. Total number of spanning tree. Okay. Now next I'll move to the next concept. So okay. So properties of trees. First. So in this class we will discuss two properties. Okay. The next class we will discuss the remaining properties. So in a tree, any two vertices are joined by a unique path. So that is the first property. Okay, in a tree, to take any two vertices are joined by a unique path. Okay. So okay, let x and y be any two vertices of T. So I will take maybe I will take here x and y. This is x, this is y. X, y are two vertices of what? Tree. Suppose there exists, I need to prove there is the two vertices are joined by a unique path, but the direct proof is here we are not going to give a direct proof. We are going to give the indirect proof. That means we are going to assume, suppose there exist two paths P1 and P2 between what? Between uh, between x and y. Okay, wow. So I'm going to, this is first path P1, like this it is going. Okay, so, so these are our vertices. These are our vertices. This is a path P1 from where? From X to Y. Similarly, next, suppose there is a two path P1 and P2. So there is another path. This is another path P2. Okay, from what? X to Y. Okay. So if P1 and P2 are non-intersecting, yes, here P1 and P2 are non-intersecting. That is intersecting only at what, X and Y. So okay, so that is the meaning. Okay, so P1 and P2 are non-intersecting. So then X P1 Y P2 X. Okay, X, this portion is called P1, and then Y, and then this portion is called what? P2, and then X is a cycle. Okay, is forming a cycle. So contradiction to the fact that what? T is a tree, because you are assuming T is what? Tree. So a tree means it has no cycle. Suppose why we get a contradiction? Because we have a cycle. Why we have a cycle? Because we assumed what? There are two paths between what? X and Y. So that's why. So case 2. Case 2, suppose the P1 and P2 are intersecting. Okay, P1 and P2 are intersecting. So maybe I will explain here also. It is explained here. Okay, maybe I'll put it another diagram. So X, Y. Here I'll put Y. So it is like this. Goes like this, and then here it is intersecting, and then it goes like this. It goes like this, and then come, and then go, and then finally it join. Similarly, this is another path. So this is P1. Okay, or this portion. Okay, this portion is P1, and then this portion is what? P2. There is another path P2. Okay, P1 is what? From X to Y. So P2 is from another path X to Y. So there is intersecting. This point I will take what? Z. Okay. So now P1 and P2 are intersecting. Okay, intersecting. Let Z be the vertex common to the path P1 and P2. So X P1 Z. So X P1 Z, and then P2 X, and then P2 X is a cycle. So again we get a contradiction to the fact what? T is a tree. So and hence, so in a tree, any two vertices are joined by a unique path. So this is property number 1. Next to property number 2, so a tree with n vertices has n minus 1 edges. So this is somewhat important property. A tree with n vertices has n minus 1 edge. So what is the assumption? T is a tree. This is assumption. How many vertices? N vertices. So we need to prove T with n vertices has, what I need to prove? T has n minus 1 edges. Okay. So okay, now proof is based on the mathematical induction on the number of vertices of V. Okay, the number of vertices of cardinality of V. Cardinality of V means the number of vertices in tree. Okay, if cardinality V equal to 1, what cardinality of V equal to 1 means? N equal to 1. N equal to 1, or just a dot. So this implies, so T has how many edges? Okay, n minus 1, because I told n minus 1. N is what here? 1. N equal to 1. So 1 minus 1 equal to, 1 minus 1 equal to 0 edges. Okay, so 0 edges. So for n equal to 1 we verified. Suppose n equal to 2. N equal to 2 means, okay, this is n equal to 2. So how many edges here have? 1 edge. So what I need to prove? T has what? N minus 1 edges. So T has n minus 1. Okay, n minus 1 is what? N equal to 2. 2 minus 1 equal to 1 edge. So for n equal to 1 and n equal to 2, the result is true. Because for mathematical induction, we will start from where? And the basic values of n. So I verified n equal to 1 and n equal to 2. Now I am assuming, so n is greater than or equal to 3. is greater than or equal to 3, and assume that the result is true for uh, true for all trees with the number of vertices is what? Less than or equal to k. Suppose a tree with k vertices have k minus 1 edges. So that is the meaning. Okay, now let T be a tree with the number of vertices in the tree is what? K plus 1. I will take it. Okay. So let x and y be any two adjacent vertices of T. So that, okay, x and y, I'll draw a diagram. So this is x and x, this is y. Okay, x, y are two adjacent vertices. And then here you have a, okay, portion like this. Here you have some portion like this. Okay, this portion. Okay, so this is okay, x and y. Now adjacent vertices. Okay. Now from T, I am going to remove the edge xy. So we'll by remove the edge xy, we'll have at least two components, say T1 and T2. So now actually I am assuming what? Assume two components. If you have three components also, we can give the proof. Okay, so I'm assuming it has two components. Suppose I am removing this edge. Okay, removing this edge, then you will get the component which containing x. Okay, which x containing what? X. Similarly, we get another component, containing what? The vertices y. So I removed this edge. Okay, so I call the first component is T1. This is T1. This is what? The second component is what? T2. Okay, so this is actually connected. This is connected, and also this is tree. Okay, okay. So there are two components. So again, I'll repeat. This portion T1 is a connected component, and also we assumed that T is what? Tree. We assumed T is a tree. Okay, T is a tree. So this is also what? T1 is also what? A tree. That means what? Connected, and it has what? No cycle. Similarly, T2 is also what? Connected, and it has what? No cycle. But the maximum number of vertices in T1, okay, is what? K. Similarly, maximum number of vertices in T2 is also what? K. Because the maximum number of vertices in T is what? K plus 1. So at least two components means maximum number of vertices, okay, in T1 is what? K. Similarly, small k. Similarly, the maximum number of vertices in T2, okay, vertices of T2, vertices of cardinality. Okay, the maximum number of vertices in T2 is also what? Less than or equal to K. So by induction hypothesis, assume the result is true for what? All trees what? With vertices less than or equal to K. Already I told that. Okay, suppose a tree with vertices is K, then by induction it has what? K minus 1 edges. It has what? K minus 1 edges. Okay, K minus 1 edges. Okay. Now, so using that idea, okay, by induction hypothesis, the number of vertices in T1, okay, is equal to, sorry, number of edges in T1 is equal to number of vertices in T1 minus 1. Okay, so number of edges, this is by mathematical induction. Number of edges in T1 equal to number of vertices in T1, okay, minus 1. Similarly, the number of vertices in T2 is equal to sorry, this is what? Number of edges. Okay, this is also number of edges. Number of edges in T1 equal to what? Number of vertices in T1, because we don't know. It is maximum K. That's why I don't want to put here what? K. Okay, K or less than or equal to K. So similarly, the number of edges in T2 is equal to number of vertices in T2 minus 1. Okay. So now we are going to calculate the number of edges in total T. Okay, total T. So next step. So the number of edges in total T. Okay, what is the number of edges in T? Number of edges in T is nothing but number of edges in T1 plus number of edges in T2 plus this edge, because xy is also in what T. So that's why they wrote what the number of edges in T equal to number of edges in T1 plus number of edges in T2 plus 1. This one is for what, the edge xy. Okay, just now we got number of edges in T1 is what? Number of vertices in T1 minus 1. I wrote here. Okay, I wrote here number of edges in T1 equal to what? Number of vertices in T1 minus 1. Similarly, the number of edges in T2 is what? Number of vertices in T2 minus 1 and then plus 1. Minus 1 plus 1 gets cancelled. So number of vertices in T1 plus number of vertices in T2 and then minus 1. So what is the number of vertices in T1 and the number of vertices in T2 if we add these two? So number of vertices in T1, because T1 contains the vertex x, T2 contains the vertex y, T2 contains the vertex y. So the number of vertices in T is equal to number of vertices in T1 plus number of vertices in what? T2. So that, and hence the number of vertices in T1 plus number of vertices in T2 is what? Number of vertices in T and then minus 1. So what we proved, number of edges in T is equal to number of vertices minus 1. That means the number of edges is equal to, what is the number of vertices? N. So n minus 1. So that is we want to prove. Okay, that is we want to prove. A tree with n vertices has what? N minus 1 edges. Okay, so now I'll stop here. In the next class we will discuss some of the problems and some more properties on trees. Okay, thank you.